Okay, let's get started. Welcome everybody to day 3 of the Learning and Testing in High Dimensions workshop. Today we have, I'm super excited about today's program. It revolves all around the theory of deep learning. And we're fortunate to have Chile from UT Austin to start us off today. Chi, do you want to share your slides?
Yes.
So
Yeah.
take it away. Thank you.
Okay. Thank you, Adam. So today I'm very happy to talk about my recent work on SGD lens one-layer network with WGANs. And this is joint work with my wonderful collaborators, Jason Lee, Alex Tamakis, and Kostis Daskalakis. So we all know that generative adversarial networks are very widely used and popular for learning real-world distributions. For instance, it creates such very photorealistic images. And among different types of GANs, WGAN or Wilson-Stem GAN is proposed to improve the training dynamics of GAN. Since with its formulation like this, it can actually minimize the Wilson-Stem distance between the real distribution and the distribution we are generating. So as normal GANs, it is a two-player game where the mean player minimizes over the generator function, and the max player chooses among all the one-Lipschitz discriminators so that it can distinguish between the real images and the generated images. And from this formulation, we can see that in order to match the real distribution and our generated distribution, WGANs actually require to solve this min-max optimization to its global optimality. However, we all know that this kind of problem is quite challenging because it's usually it's non-convex, non-concave. However, in practice, some simple heuristics like stochastic gradient descent ascent usually performs well in practice. So this there naturally arises question that are GANs able to learn high-dimensional distributions in polynomial time and polynomial sample complexity with simple heuristics like stochastic GDA. And in this work, we are trying to answer these questions with a very simple setting as a starting point. But first, let me review some prior work. The prior work usually look at the optimization and the statistical side of GANs separately. So on the optimization side, people have proved that under some settings, they can show local convergence. And for general min-max optimizations, there are also some studies. Mostly for global convergence, they can only show for non-convex concave or convex concave setting. And there is also some local algorithms that achieve local optimization for non-convex, non-concave objectives. And on the statistical side, there are proposals to kill the mode of collapse, and I'm not listing all of them. So all this work, almost all this work look at optimization and statistical side separately, so they cannot actually show that simple heuristics actually learn the algorithm. And one exception is Fizzy et al. 2017, that they can show that with linear and the quadratic discriminators, we can learn Gaussian distribution. But Gaussian distribution might not be good enough for us to understand GAN. And in this setting, we take a further step by studying one-layer generator. So we study the generator of this form. So GA is parameterized by a matrix A of dimension D times K. So it maps from the input of Gaussian distribution of dimension K to output image of dimension D. And the form of the generator is just a linear map composite with a nonlinearity. So the nonlinearity can be arbitrary, like 10H sigmoid value, leak value, etc. And we study the proper learning setting, meaning that for the real distribution, there exists a corresponding A star such that it matches the target distribution. And our problem formulation simply becomes this. So as we said, we parameterize the generator by matrix A, and we will parameterize the discriminator by a vector or a matrix B. And we naturally are doing the min-max game like this. But now, one important question to ask is what kind of discriminator class should we choose to learn the real distribution? From the design of WGAN, we see that we should choose the discriminator of all Lipschitz-1 function. But of course, that will be too computational intractable, and actually it's not needed. Actually, the choice of the discriminator class should attain a subtle balance between those different properties. First, it should have enough identifiability power. So meaning that it should be large enough so that GA, which is the maximum over all the discriminator functions, will have an optimal solution that matches your target distribution. If it's too simple, you cannot identify the target distribution from this kind of function. And in our setting, what is our target? We are actually trying to learn A star transpose instead of specifically matching A star, because the input is from Gaussian distribution and has some symmetric property. So if we rotate the input by a matrix U, the target distribution doesn't change. So we might not be able to exactly learn a specific A star, but as long as we learn some A, such that A transpose equals to A star transpose, that's fine. And the second, the discriminator class, we can see that to have enough identifiability power, all Lipschitz-1 function naturally is enough, but that's not what we want. It should also be small enough so that we can learn with fewer samples. So we want to attain generalizability. And third, we also want to attain stability, meaning that simple heuristics, local algorithms like gradient descent ascent will converge, and hopefully will converge to global optimal point. So now let's see how we can design the discriminator and how we can possibly learn the distribution. So first, we will study the population risk, meaning we have infinite number of samples, and this part just help us to understand the optimization side, and later we'll move on to finite sample case. So as a warm-up, let's first look at how to learn the marginal distribution. So recall our function will be a min-max game over this kind of function. And to learn the marginal distribution means we want to match the distribution for each coordinate of the xi. And from our design, each xi actually follows a distribution like this. So it's naturally a Gaussian distribution with mean 0 and variance ai's norm squared. Ai is the i's row of matrix A. Recall A is dimension D times K. And xi will just follow B composite with this Gaussian random variable. And in this case, we can see to learn the marginal distribution is to recover each norm of AI squared. And in other words, it's the diagonal part of A star transpose. And so for the three different properties, we can see now that in order to identify the marginal distribution is exactly equal to recover each norm of AI. And also in order to achieve generalizability, we start to think from the simplest discriminator class, which is linear discriminator class. Let's see whether we can recover this AI. So For linear discriminator, the function naturally becomes dvx equals to v transpose x. And so our function becomes something like this. It is trying to match v transpose x with the v transpose v, the generated variable. So in this form, we can see that linear discriminator is trying to match the first moment for the distribution. And for some kinds of activation functions, this is actually enough. Yeah, sorry, I took a look at the chat channel. For something like ReLU or leaky ReLU, so this is enough, because for different choices, the choices of AI's norm, the mean of X and the phi AZ will be different. And to match the mean of X will actually give us the norm of AI. But for some other kinds of activations, like all functions plus constants, such as sigmoid and tan-H, actually, due to this symmetry of Gaussian, the expectation of X or Px will remain the same for different choice of AI's norm. So in this case, we use rectified linear discriminator to create some non-symmetry, such that for different AI's norm, the mean will be different, so that if we match the first moment, they will still be the same. And thirdly, about stability. So there are some prior work that say that if the min-max problem is linear in the max part, it will we will not yield last iterate convergence. And luckily for WGANs, we actually have some constraint on the discriminator. So remember, we should look at Lipschitz 1 function. So this is essentially some kind of regularizer on the discriminator class. And we choose to use a simple version of it, which is we minus some L2 regularizer to it. And luckily with this form, the max part naturally becomes the L2 distance between the mean of the real distribution and the mean of generated distribution. And this actually make the min-max problem very, very nice to be solved. And to conclude on the marginal distribution side, for activations including leaky ReLU, subclass sigmoid, and tan-H, all the station point of the F1 we talked about will yield parameter A such that AI's norm matches the target distribution's AI's norm. And on the stability side or the convergence side, we can also show that gradient descent ascent can converge to the global min-max point such that it matches this kind of properties. And then, so next, let's move forward to look at the joint distribution. From the previous design of the discriminator class, we can see that there is no interactions between each coordinate of X, so there was no hope to learn the joint distribution. To proceed, we want to add such interactions between the coordinates. So natural idea is to look at quadratic discriminators. And actually, quadratic discriminator can capture the covariance of the target distribution. So let's see. The discriminator looks like X transpose Vx, and we can also write it as the inner product between XS transpose and the parameter for the discriminator function, V. Therefore, again, with regularized version, the max part can be written like this. So in order to minimize this function, it's actually equivalent to matching the second moment of the target and learned distributions. And to proceed, we need to study the geometry of this function. Luckily, with the help with Hermit, extension, we can write out this function as something of this form. So if we write a function phi, the activation function, as the summation of some coefficient times each Hermite function, then we can write GA as the summation of each Hermite coefficient squared times A transpose to the Harvard of power I minus AA transpose to the Harvard power I. This is because of the following property of Hermite expansion. So for any functions that can be written as the Hermite expansion, if the input is Gaussian, is unit Gaussian, then the expectation of phi U transpose V times phi of V transpose Z can be written as summation of the Hermite coefficient squared times U transpose V to the i's power. Therefore, with the same thing, we can write out GA as the following form. And from this form, we can see that there are some very good properties. Because only AA transpose plays a role here. So we can actually do the following reparametrization, that we write out Z equals to AA transpose and Z star equals to A star transpose. Then we write GA to be this following form. With this form, a very good property is that each coordinate of Z is contributing separately to G. So we can write out G tilde Z as the following form to be summation of G tilde JK. So each coordinate, each J's row, K's column of Z, and that's the following form. This is good because for such scalar functions, it is much easier to study its stationary point. And actually, we can find out for some classes of activations. For example, odd functions plus constant and the leaky value. This function satisfies that all stationary points are global mean, meaning that all stationary point must have Z matches Z star. Therefore, on learning the joint distribution, we can show that for activations including leaky value 10H sigmoid, G tilde Z has a unique station point such that Z equals to A star transpose. And in this case, gradient descent ascent also converges to the optimal solution that matches A star transpose. Notice that if once we learn this A star transpose, we have learned the target distribution. So then let's move on to the finite sample case. So we're interested to know with polynomial number of samples, but we can still learn the joint distribution. So in reality, we will use a finite batch size. We don't have infinite computational power. So for each iteration T, we will generate Z1 through Zm. The batch size is M, number of samples from Gaussian. And we also use sample size N of the Xi from the real distribution. And our min-max optimization essentially becomes gradient descent gradient step over this G tilde Mn, Mn to indicate the finite batch size and sample size. So the difference from previous function is just we replace the expectation by the finite sum case. Yeah, so we match this. And with this form, we can also show that with sample size n, batch size m, to be large enough to be poly D over epsilon squared. Then for large enough T, stochastic gradient descent ascent also converge to the global minimum point. And the learned AT transpose will be close enough to A star transpose. So here we have the absolute value of the distance because we assume A star has a unit norm. And actually this dependence on 1 over epsilon squared is optimal because there is some prior work that shows a lower bound of order 1 over epsilon squared on learning such generative models. So the proof sketch is a little bit complicated and looks like this. So remember that our target is to minimize over this GA that matches A star transpose with AA transpose. And it can also be reparameterized to GZ. And our gradient step is actually on GN, which is the expectation over the samples from the Gaussian distribution and the finite sample case. So the proof sketch roughly is the following steps. First, it's very easy to see that stochastic gradient descent ascent and WGAN will be essentially SGD on this GN. And with some prior work, Li et al. And G et al., we can show that stochastic gradient descent will find epsilon second order station point of Gn in polynomial time. And for large enough Mn, so the epsilon stationary second order station point of Gn actually will also be order epsilon station second order station point for this population risk of A. And the second order station point of GA actually will be the first order station point of G tilde Z, the reparameterized form. And G tilde Z, as we talked about previously, has some good property that it has a unique station point of A star transpose. So order epsilon first order station point satisfy Z minus A star transpose is also of order epsilon error. Therefore, for large M and N, so altogether we have stochastic gradient descent ascent on WGAN with quadratic discriminator function will find A such that it's not too far from the target A star transpose. And in conclusion, our work study both the statistical side and the optimization side jointly so that we can show simple heuristics like gradient descent ascent, find the target distribution. On statistical side, we say that discriminator match low order moments, which avoids curse of dimensionality. So this seems simple, but it's easier to take a further step because for discriminator classes like neural network, it can actually approximate arbitrary many higher level polynomials. Therefore, it can naturally learn larger class of generator functions, as there is some follow-up work, Li and Do shows that. However, of course, for higher moments, it's harder to get optimization results. And on the on the optimization side, we show that with simple discriminators like linear or quadratic functions, stochastic gradient descent ascent can help us achieve global convergence. And and also adding regularizer like WGAN does will stabilize the GAN training and make sure that simple heuristics work. And to go beyond simple GANs, we will be studying the training dynamics instead of as what we did to learn the geometry of the functions, especially if we want to tackle for non-convex, non-concave min-max problems. And that's it. Thank you.
Okay, thank you. Any questions for Chi? Feel free to unmute yourself if you're on the panel or raise your hand in the Zoom chat. I have a question for you. So is there any hope that Some of these papers that you're referencing actually learn one hidden layer, so you have, a sum of ReLUs or a sum of leaky ReLUs. I mean, is there any hope that you can extend this work to a model where you have, a, a matrix A times phi of WX?
Uh,
Um,
yeah, so on this statistical side, it's definitely hopeful and it's already done as here, like Li and Do, they actually showed for one hidden layer generator model. So it's actually in the same vein of matching higher order moments. But for optimization side, it might be hard.
is the issue that for these higher order moments, you lose that nice little Hermite formula that you have?
Yeah, yeah.
I see. And so it's sort of a stumbling block there, I guess.
Yeah, so the output is not separable, so it's very hard. Mm.
I see.
Yeah,
Interesting.
for more complicated generators, we will definitely need more complicated discriminator, which makes the problem non-convex, non-concave. And generally, we actually don't know how to achieve global min-max for general non-convex, non-concave problems.
Right.
There are work, as I mentioned in the related work part, to achieve local min-max, but that's not enough for us to learn the target distribution in general.
Gotcha. Any other questions?
So I see that Vinay asked, does your theory tell us about good nonlinear functions for learning distributions? So yeah, so it's a good point. So as we see here, so linear and the quadratic discriminators is very simple, but it gives us the sense that the discriminator can help us match the moments. Therefore, as I mentioned here, for neural networks that can approximate higher order moments, higher order polynomials, we can naturally match higher order moments. Therefore, we can also learn more complicated functions. So it's on the statistical side.
Okay, well, thank you again, Chi, for a great talk. And we'll resume in 2 minutes. So enjoy enjoy your 2 minute break.